All right, so hi and welcome back. So we are looking at roots and weights again. So I'll just remind you quickly of what roots are and then what weights are, and then we shall go on to look at the rest of the what else I had in mind for roots and weights. So the idea was that we wanted to generalize the discussion of SU2s and the representation of SU2s for arbitrary simple Lie algebras. And what we are going to do out here, as I said, is that we would be trying to label our states with the largest set of commuting Hermitian observables. Uh, that is the eigenvalues of this largest set of commuting Hermitian observables. So these would be so first we need to identify this set, and this set of commuting Hermitian operators, which is as large as possible, is what is called the Kartan Sub Algebra. And if we are looking at some particular reducible representation D, there will be, say, hi of them, where I runs from 1 to n. So these are the uh, I mean Cartan generators. We're going to call them hi. So hi is equal to hi dagger because they're Hermitian, and hij is equal to 0 because they are commuting by definition. So this we can choose a basis where they will satisfy hij is equal to trace. So trace hij will be delta ij up to some numbers in front of it. Okay. Now the number m, the number the uh, uh, total number is, as you remember, called the rank of the algebra. And we said that so the states are going to be, so these states are going to be labeled under the weights of these HIs. So let this be a state, and these the eigenvalues of the HIs will be called mu i's, and mu i's are what will be called the weights. Okay, very good. Now so mu I is called the weights, and m component vector with mu I as its as the m components will be called a weight vector. Now when we are looking to understand roots, we would look at specifically at the adjoint representation. So now remember that you were so TABC is IFABC. This is what the adjoint representation is. And so you are, so the very important thing is going to be that the states of the adjoint representation corresponds to the generators themselves, since these rows and columns of the matrices are labeled by the same index that labels the particular generators. So you can denote this by by the state corresponding to an arbitrary generator XA as XA, and then we use that to prove various things, like the generator XA acting on the state XB was the state which was given by the this bracket of XA and XB. Okay. And as I tried to highlight last time around, and I'll also do this here again, so the roots would be the weights in the adjoint representation. Okay, so that is going to be what the roots are. And so then again we did various things. We saw that since the hij is equal to 0, the states that correspond to these Cartan generators have 0 weight. Okay. And moving on, what we found is that those which do not do not correspond to this Cartan generators, they effectively so that is going to uh, give us something else. All right. excuse me. So these corresponding generators, so they would have some I mean non-zero weights, and these I mean generators will satisfy hi e alpha is ei, I mean alpha I e alpha. These non-zero weight vectors will specify uniquely these states. Okay. Now there'll be a lot of SU2s hanging around. So these the first hint at that the fact that you're going to get something like raising and lowering operators is when you look at look at trying to find out what the Hermitian, I mean Hermitians, Hermitian whether or not E alphas are Hermitian, and you find that they are not, and what you find is E alpha dagger is equal to minus E alpha, and this is are very much like the J plus minus of SU2. Now remember, these are E alpha, so these yeah, so there are a host of them. But okay, so now so again there is a root vector which is equivalent to this weight vector, but in the adjoint representation. So okay, now the other thing that we found is hi with this particular, I mean, operation shows you that e plus minus alpha actually raises or lowers the weights by plus minus alpha. At this point, we don't really have a notion of what is going up and what is going down, so it does not make sense to ask what is raising and what is lowering. Interestingly enough, when you do E alpha acting on E uh, minus alpha, this by the virtue of what we have just seen is going to be this is going to have a weight 0. So if it has a weight 0, this has to be a linear combination of states that correspond to these HIs, right? And if then if you do the algebra, what you find is E alpha with E minus alpha is alpha dot H. This should remind you of the relation of J plus with J minus equal to minus 3. I mean, sorry, J plus, I mean J minus is J3. Now, as you can understand, there are a lot of SU2s. Okay, so for each non-zero pair of root vectors, there is going to be an SU2 algebra with these group generators. So let's just look at this. So so this each non-zero pair of root vectors here, this I mean corresponds to an SU2 algebra. So these E plus minuses I have now I mean relabeled. I've absorbed the alphas in, and I've called E3 as something which is alpha to the power minus 2 uh, uh, with, I mean, alpha dot H. So it should be very straightforward to now see that firstly, if you're looking for E3 with E plus minus, when you just do take these particular normalizations into account, you will find that this is just E I mean plus minus E plus minus. And and what you'll also find is if you look at E plus with E minus, you are going to get E3. So this is an SU2. So you are going to get an SU2 for each alpha, right? Now we know that if you on general grounds, that states of each irreducible representation of the full algebra can be decomposed into irreducible representations of any of these SU2 subalgebras. And as we have been saying, we know everything about the irreducible representations of SU2s. So this is going to put a very strong, I mean, very strong constraints on the nature of roots. For example, we can actually prove, this is not something I'll do out here, that root vectors, I mean, actually, I mean, correspond to unique unique generators. Okay, this I will actually for you to prove. um, Okay, so now moving on, what we want to do is we want to now figure out what is going to happen. So so we want to sort of try and see what are these strong, constraints on the roots that you get from here. Okay, so now you have so for any weight mu in a representation D, this E3 value is going to you'll get E3 as this, right? So this is something again that we know. So this is just, yeah, you just remember what the definition of E3 was, and it'll just follow from there. H gave you just mu, so E3 is going to give you alpha dot mu by alpha squared. Since this has to be so what you again you would remember that just you take lessons out from what we had done in our SU2 examples earlier. So the E3 values need to be integers or half integers. So twice of alpha dot mu by alpha squared is actually going to be an integer. Okay, this is going to be very important going forward. Uh, so what we will see here is so general state can be this state that we wrote down earlier, can be written as always be written as a linear combination of states that transform according to some definite representations of SU2 that are defined with E plus minus and E3 that we have actually seen earlier. And now let's suppose that there is some highest uh, spin appearing in the in this particular linear combination, which is J, and there is some non-negative non-negative integer P, such that if you raise this thing, if you take the state and raise it to this power and act on it with e plus uh, p times, this is going to be non-zero, and this will have a weight mu plus alpha p. Uh, and this is going to be the highest weight state of highest weight state, where the weight is of E3 of this SU2 spin J representation. Okay, so that means that if you take this state and act it with EP, if you take this whole state and act it with EP once again, E plus once again, that is going to be 0. So E plus P plus 1 acting on this state is equal to 0. Okay. Now the eigenvalue of E plus P acting on mu D is going to be given by this is going to be alpha times mu plus alpha p by alpha squared. So this is going to be the J. This is going to be the J of that state, right? So this means that what you have is, for this highest weight state, this is what we have. Okay, so this is J. This is the E3 eigenvalue. This is J. Similarly, you can get some particular non-negative integer q, such that you can act on this act on the state q times with this e minus, and this is going to be the lowest weight state of the SU2 spin J representation. Again, if we look at this, then the weight of this guy is going, E3 weight of this guy is going to be alpha mu minus q alpha by alpha squared. And this has to be equal to minus j, okay? So again, like what we did for the SU2, we are just using this for a particular alpha. Very good. So for a particular root, okay? So what we have is that one of the relations is this, and the other one is one we have here. The other one is here, and we can add them up if you wish. And once we add them up, what we see is that we have something which is 2 alpha dot mu by alpha squared plus p minus q equal to 0. Or this particular thing, this uh, this formula we can call the master formula, okay? So as innocuous as it sounds, as it looks, it actually is very powerful, okay? So this can be very useful, and this is going to lead to a geometric classification of all compact Lie groups. As I said, it doesn't look like much, but it can be used to great effect. So let's look at this and let's try to use this on some roots, okay? So instead of so let's apply this on roots. So now let's look at we are going to use it twice for any distinct pair of roots alpha and beta, okay? So so what we are going to do is if we define the SU2 with E alpha, then we can use this, and this is going to be alpha dot beta by alpha squared is this minus half p minus q. And if we define the SU2s with E beta, then this gets interchanged. So beta dot alpha by beta squared is minus half some other p prime minus q prime, okay? Now you take this and you take this and you just multiply the two, right? So if you do that, then this is pretty remarkable. Remember that this is these are two vectors alpha dot beta, and so this is going to be, in that case, this is going to be the angle between the two roots alpha and beta. So this, what we get is cos of this angle of, so if you multiply this guy and this guy, what you're going to get, the right hand side is going to be the cos of the angle between the two roots alpha or beta, square of that. This is just alpha dot beta the whole square divided by alpha squared beta squared. This is equal to q minus p, p minus q into p prime minus q prime by 4. Remember that all of these guys, p, q, p prime, q prime, were integers. So p minus q is an integer, p prime minus q prime is an integer. So the product p minus q into p prime minus q prime must also be an integer, and it also has to be non-negative, as we have seen, right? So what have we got? So it's this is a squared, of course. So what have we got then? So this has to be a non-negative integer, and it's also the square of it's also cos squared of alpha beta of theta of alpha beta. So let's see what that gives you. So you can start off with so there are only 4 interesting possibilities for the angles between the roots, okay? This can be equal to 0, whereby theta of alpha beta will be equal to 90. This can be equal to 1, where theta of alpha beta is 60 or 120. It can be equal to 2, where theta of alpha beta is 45 or 135. Or it can be equal to 3, where it's 30 or 150. The thing that is equal to 4 just makes it 0 or 180, which is trivial, since the roots always sort of come in pairs, and both of them both are in the same SU2 subgroup. Okay. So what we have done is we have used just the representation theory of SU2s to actually nail down what all the angle between roots, roots could be. Okay. So this is rather remarkable and rather nice. And again, I urge you to go through this in a little more detail, and with some with some more slowly. I that would be that would be a good thing. But before I end today, I wanted to give you a slight glimpse of SU3. Um, After SU2, actually, this the most important algebra in all of physics, especially in particle physics, is SU3. It may actually be even more important than SU2. Again, so this is SU3 is the group of 3 cross 3 unitary matrices with determinant 1. And it's generated by 3 cross 3 Hermitian traceless, traceless matrices. So if we exponentiate, Hermitian matrices to get, if you start off with this, then you can compute the determinant in any basis. In particular, if you want to sort of, diagonalize this alpha a x a, then let's do that. Then what we have is, that diagonalizing matrix v inverse. So this becomes D, which is which is going to be diagonal. So determinant of U is determinant of exponential ID, which is the product of I djj. So this is just the trace of D. Now remember that the trace is going to be the same for D or for XA, alpha XA. So if the trace of alpha AXA is 0, that means the determinant is equal to 1. So this is sort of way to see that the that one of them gives the other. So the tracelessness, actually leads you to having SU3 here. Okay. So the standard basis for 3 cross 3 Hermitian matrices is a generalization of Pauli matrices, which are called these Gelman matrices, and these are of the following sort. So lambda 1, lambda 2, lambda 3 are of this sort, as you can see here. This is I, if this is not clear. So this one is I. Okay. This is I. Not sure I'm doing the best job. Yeah. So lambda 2 is so lambda 1 is 0, 1, 0, 1, 0, 0, and 0, 0, 0. So you see that the first 3 of these guys are things which are Pauli matrices with an extra layer of zeros attached to it. Okay. And if you wish, the next ones are sort of like the uh, uh, so yeah, the next ones are also, you have inserted stuff here, so you can see that these are also sort of like I mean generalizations of the Pauli matrices. And you have yeah, I mean, one of the things that you need to keep in mind is that, these have to be uh, eight. I mean, there has to be eight of them because it's SU3. SU3, so the number of independent entries would have been n squared. If not, so SU3 would have, I mean, if you had U3, that would have just been, 9, but you have SU, so that's another, I mean, extra thing here, extra, I mean, extra condition. So that means the number is less by 1. So the number of independent generators is going to be n squared minus 1 for it, for this case. And in this case, since it's SU 3, so that means 3 squared. What am I doing? I'm sorry. So that's SU3. So would mean 3 squared minus 1. So that's 9 minus 1 equals 8. So there has to be 8 of these guys. So that's a way to, so this particular set of eight matrices is sort of something that, I mean, generalizes the Pauli matrices. And so yeah, so that's that. And so in the same way, you can think about trying to I mean, go on and find out 4x4 matrices and so on and so forth by this. But yeah, so that's one way of trying to do it. So what you do is you define the SU3 generators as TA is half lambda A, where these lambdas are the ones on top. And you'll see that these will satisfy TA TB is equal to half half delta AB. Okay, so it's convenient to put T3 in the Kartan subgroup, I mean sub algebra, and that would also mean that you're also going to put, I mean, T8 in that as well. So H1 and H2 is going to be T3 and T8. So now so now life becomes simple. Uh, the weights of in this particular representation are very easy to find because T3 and T8 are already, I mean, in the diagonal form. So this is half minus half and 0, and T8 is this matrix. So the eigenvalues and the associated, I mean, eigenvectors are very simple. So it's 1 0 0, which corresponds to half and root 3 over 6, um, and then 0 1 0 with this entry and this entry, and 0 0 1 with this entry and this entry. So that's that. So if you try to plot these vectors in a plane, these form the vertices of an equilateral triangle. So this is given by H1 and H2. So the roots are going to be the I mean difference of the weights, and as the corresponding generator must move us from one weight to the other. So the corresponding, I mean, it's not very hard to see that the corresponding generators are those which have only one off diagonal entry. So these are going to be, so E01 is going to be T1 plus IT2, And so you'll I again so this is something that you should be able to work out on your own. So the roots are going to be roots are going to form a sort of uh, regular hexagon where at the center you have these two uh, two particular elements of the sub I mean of this Kartan sub algebra. Okay, so yeah, this last bit may have been a little fast, but again, the general lesson that I want you to I mean take away from this is that the idea is that the uh, what you so the representation of SU2 is extremely important because it is going to help us build things for all others simple the algebras. Okay, so and I've shown you how to do that. I agree that I've not been very so I've not gone into a lot of details, but at least it should give you an idea of what we have to do for the other groups. And those of you who are interested in trying to understand this further can actually look more. And I would suggest that you guys look at Howard Georgi's book for this part of these lectures. It's basically out of there, and you can follow and you can go further with this. Unfortunately, even though I would like to do it, I would not be able to do much more here. So with that, I think what we would do is we would stop here for the day, and so we are going to be left with just a little bit more, and in group theory, those would be a few lectures on STR, special theory of relativity, and the Lorentz and the Poincaré groups and algebras. So that will form the end of the group theory part of this course. Okay, I can understand that some of you may be little overwhelmed by a lot of this that has been going on, and some of it has been a little quick. I would urge you to try and also augment this by reading some of the books that I mean, suggested for the course. And again, as I said, for this part of the course, I've been following this last few lectures. I've been looking at Howard George. I suggest you do that as well. And this can be found in any reasonable uh, textbook on group theory, uh, on Lie groups and Lie algebras. Okay, that's it for the moment, and so we will see each other soon. Thank you.